Hey everyone, Gwen here from Nile. And today I want to talk a bit about AI and especially how to even get started with understanding what in the world people are saying about AI. Everyone has been talking about, and my friends and colleagues and co-founder kept sending me interesting tweets, interesting blogs, interesting articles. And I had a really hard time even reading what they're sending me because I couldn't quite get the terminology. And when I said, well, can you help me understand, it says transformer here, what does it actually mean? They'd send me this paper. Now, I like reading papers, but it didn't make sense for me to read a paper for every word I'm trying to understand in a short, 256 character tweet. So I did the work. I read everything. I read the papers. And let's be frank, most of it is not actually all that complicated. So I thought I'll do a quick video, and I also did a slightly longer blog, just going over the common terminology and demystifying it a bit and saying in plain simple English what does each word mean, and also which ones are actually useful versus which ones are slightly more buzzwordy. And then I'll give you a bunch of pointers so you can follow up and actually read the papers if you want to, because the papers are good. So let's get started. The entire hype started with ChatGPT. What is ChatGPT? It's a chat interface on top of a family of models called GPT. GPT is generative, pre-trained transformer model. Generative means it actually generates text. This is different from older models that you may be familiar with that do things like recommendations. Those don't generate, they just recommend pre-existing videos on Netflix. Pre-trained, meaning that the model has been trained in advance on giant corpus of text. So the model is already trained. You don't have to further train GPT models. They are very well trained in advance, although you could. We'll talk about it in a second. And the last bit, transformer model. So transformer is an architecture type for these kind of models. It's a type of neural network. But the important bit is that it knows how to interpret sentences in a holistic way that also takes into account context and the order and placing of words in the sentence. And it does it both on the input, where it's trying to get a sense of the entire sentence and not just pull words out of context. And it's also doing it on the output, which is why the output is usually very good, very grammatical English, because words appear in context because of the way those models are built. So when you use one of those models, especially if you use something like ChatGPT, but even if you use them through the API, there is a sense of a conversation. You ask a question in English, you get a response in English. And the question side is often called a prompt. A lot has been said about prompt engineering. In my experience, it actually matters. Why, if you say things differently, you will get different responses, sometimes dramatically different. And I have an example for that in the blog. So prompt is the question. The answer is sometimes called a prediction. And at first that really confused me. Like, why are you telling me that I'm using the model to predict something? It turns out that it's called prediction because it's the way the model works. It's trying to predict the next logical, high probability word to present to you in the sentence. And it's obviously taking quite good guesses, enough to fool us to believe that it actually thinks something. That using the model in general is also called inference. This is to differentiate the part of the process where you use the model to answer questions from what happens before, which is called training. So you have the training phase in the life of a model, and then you have the inference phase. About those pre-trained models that have learned the entire internet as of 2023 by heart, is that they're really good at answering those general questions based on knowledge of the entire internet 2023. But if you need an accurate answer that is based on specific data sources, and you even have the data sources in hand, hey, please answer my legal question based on this case law, do not use Reddit legal advice as a source, then this actually gets a bit harder. And the more specialized you want your answers to be, the more accurate you want them to be, the harder it gets. There is two main techniques used in that, and you can actually combine them. And these days, it's quite popular to combine them. The first one is fine-tuning. What is fine-tuning? Remember that those models are pre-trained, but they're also built in a way that allows you to continue training them. So fine-tuning means taking a very large corpus of question and answers, a textbook, Stack Overflow, LeetCode, all of those are good sources of question and answers. And then you train the model on this set of question and answers. And then when you ask the model further questions, you ask it for more inference, it answers based on the additional training you gave it. Now, this is a lot trickier than it sounds like. Because it takes a lot of resources. And when people talk about models requiring a lot of GPUs, being expensive, taking a lot of time, they usually don't talk about the inference. The heavy lifting is the pre-training and then the fine-tuning. So if you want to fine-tune, especially a large model, you'll need serious resources. One problem. Number two is that there is a lot of algorithms for fine-tuning. In order to understand what gives you good results, you need to experiment. You need a way to evaluate the model. Did I train it enough? Am I happy with the way it's trained? Is it production ready? And you need a good way to track all the experiments. You need some kind of a source control. So this requires tools, it requires patience, it requires specialized knowledge. So fine-tuning is great, expensive and not simple. The other method is orders of magnitude simpler. It is called RAG, retrieval augmented generation, which instead of fine-tuning the model on huge number of question and answers, you are promoting the model with focused bit of information that you know in advance is going to help get the answer you want. There is research showing that this gives orders of magnitude better result compared to just using something like GPT. If you say, please explain to me the use of database in a specific code base, if you can actually give it the relevant bits of this specific code base, it is going to give you much better results than if you just say, explain to me how GitHub uses databases, where it will most likely hallucinate and make things up because it's not going to actually be able to find the answer. So if you have a focused question, giving this focused information as an input to the model as part of the prompt is fantastic. We call this technique RAG, and it's been proven to be effective, way cheaper and simpler than fine-tuning. So let's talk a bit more about RAG. If you give the model a really good source material, it is very likely to give you a very good answer. If you give it crappy source material, you will get crappy answer. Garbage in, garbage out. This basic rule of engineering has not changed. So usually what happens is that you have a very large collection of source material in some kind of format, maybe even multiple formats. You have some stuff maybe on a company wiki that you want to train it on, some Slack conversations, some Google Docs, some PDFs. So you have to get all this data, and then you have to prepare it. PDFs have to turn into text. If you have images, you probably need to extract the images. Questions on and answers on Slack probably have to be cleaned up a bit. You may even want to anonymize them. So you have all those data preparation steps just to make sure you have a good format. And then you need to do something called chunking, which is to get the data into a reasonable size bytes. And they can be overlapping, but they have to be reasonable sized. First of all, no more than something like 8K, maybe even 4K, with the reason that a lot of models, even till today, they will not accept very large prompts. So you have to keep this, you're going to put this data in the prompt, so you have to keep the size down. The other bit is that, as we explained earlier, the more focused the hint is, the better the answer is going to be. As you have to cut it into small bits that ideally have a cohesive context to them. Again, looking at code as an example, you will want classes or functions as the thing. If you're looking at a paper, you probably want to cut it into paragraph, since each paragraph is, in a well-written paper, supposed to have a single idea in it. The next thing is that you need to store those in a way that will allow you to find the relevant chunks later when you need them. So when someone asks a question, you will say, go to this database, look for the correct chunks, find few chunks that are relevant, and then you can put them as part of the prompt, and the AI will use it to answer the question. There is two ways for us to find the relevant chunks of text in a database, and then there is a hybrid method. Method one is the old school one, full text search. You all know it, that Elastic has made good money building a full text search database. And these rely usually on algorithms that use word frequency, how common this word is that you're looking for in each chunk. They use things like lexical similarity. So if I say ice cream, it's kind of similar to cream. The best algorithm for those these days is called BM25. And this is one way to get relevant chunks. The other way to get relevant chunks, which is very popular these days, specifically for RAG, is called vector search or semantic search. And the name hints at what it means. This method uses AI models, exactly transformer models, but instead of being trained to answer random questions, it's also trained on the entire internet, but it's trained to encode similar sentences as vectors that are close to each other. So those models take your chunk of text, turn them into a vector, vectors that represent ideas that are similar to each other, that are close together in this gigantic multidimensional space. So the models that do these things that convert text to vector, the vector is also called an embedding, and the models that do it are also called embedding models. You take all your chunks, you convert them to vectors, you store them in a vector store. There is many vector databases because this method is so popular. I've used very successfully PG Vector, an extension for Postgres. Everyone knows and loves Postgres. I know and love Postgres. Using PG Vector was a snap. So we'll use that as our vector database. And you store all those vectors. If it's a really gigantic number, you may create an index on them. And then when you get a question, your application gets a question from someone, you also convert the question into a vector, and you use a vector distance algorithm. That can be normal Euclidean distance that you learned about in school, or the more popular cosine distance. So you use cosine distance to find the closest vectors to your question, and those will be the most similar, hopefully the most relevant. You take those and send it to a GPT type model and say, here is a question as a helpful assistant. Please answer this question and use as a reference this chunk of text that I just pulled out of my chunk store, my vector store. And because those are relevant, it should allow the chat model to answer in a way that is a lot more relevant. Now, the third approach is hybrid. And there's actually two ways to do hybrid. One of them is basically to use both. So you'll go to your vector store and say, based on this vector, give me the 10 closest vectors. And then you go to a full text search and says, based on this bit of text, give me the chunks that are closest to it, that match it the best. Now you have both responses, and you can kind of sort them maybe by some kind of which one has better score. and then pick the top 3 and give them to the GPT model. That's one way to do it. Now, there are some embedding models, very few of them, that actually combine the two methods already, that can encode in ways that kind of combine the two ideas. They generate multiple vectors. They're supposed to be a lot more sophisticated. One of the nice things of using as your vector store Postgres with pgvector is that Postgres also have extensions for text search. So starting to play around with it is fairly low bar versus if you pick the database that only does vectors, then you need to pick a database that only does text, and what the hell are we doing here? So we mentioned that vector databases can search by distance, vector distance. One other thing to know is that they can also create specialized indexes for the data in the vector database. So if you have a gigantic set of vectors in the millions, then having it, it's a good idea to have an index so you will not have to scan millions of vectors in order to find the nearest one. Now, the thing about vector indexes is that they are very different than any database index you've ever worked with. It's not like Bittree, it's not like a hash index, it's not like a bitmap, it's not like anything else at all. Because they are actually a machine learning based data structure that will do an approximate nearest neighbor search on your set of vectors. So when you index the data, you actually train a small model. If you use a normal index, like a Bittree index, it's going to give you a results that are as accurate as a full table scan. Maybe they'll be faster, maybe they'll be slower. It's hard to optimize the database, but they're not going to be any less accurate. You don't lose accuracy with a normal index. With approximate nearest neighbor index, it's approximate. You lose accuracy. It basically, the main idea is that it starts by looking at the entire vector space, finding this neighborhood of vectors that looks like a good candidate. So it finds like few of those, and then it continues to refine the search within those. If this initial choice of neighborhood was off, it will not find a good match. And even if you have a perfect match in your store, it will not find it. So sometimes this is called a recall problem because it looks like your database suddenly forgot information that you put in there. And this is because of the way those indexes approximate things. Well, unless you actually need those indexes, I would say don't use them. Only use them if you tested and you get good performance out of them. Okay, so let me quickly walk you through an example just so you'll see that getting started with RAG is actually fairly straightforward. And then there will be another video where I go through full-fledged how to build an AI coding assistant from start to finish, including fancy UI and everything. Basically, I started with some setup. So I'm using OpenAI's text embedding 3 large. Fairly good. I'll explain next blog post how I picked that one and what else did I try. And then I need a bunch of API key. I need my OpenAI API key, and I need my Nile username and password. So I'm setting this up, and then I'm setting up a connection to OpenAI for the embedding model, and setting up a connection to Nile for the Postgres database. And then I'm just putting in some documents, hard-coded, since this is a short example, and starting to do interesting things. I'm calling the model and saying embed documents. Embedded documents, I get back a bunch of vectors. Take the vectors and insert them into an embeddings table that I just created in the database. Store them. Now I'm taking a question, embedding the question. Now I have another vector. This is the vector that represents the question. Going back to the database, doing select ID from embeddings, order by whatever is closest to the vectors that I got from my question. All makes sense so far, right? I got a response back. This is the embedding closest to the question. I take the ID, look at my documents, take the right document, and show it on the screen. If you have a Nile account and OpenAI account, you can just take it and get started. So super straightforward, and we'll obviously show you how to go from this 30-line code snippet to a real application. Now, if you're going to build your application for software as a service, there are a few more things you should be aware of, and we'll also talk about them next time. The first is scale and elasticity. If you're going to build software as a service, you're usually building it for some number of customers, maybe 3, maybe 500,000, but you're going to have some number of customers. You'll want to be prepared to grow in this way. Now, the different customers may be of different sizes. So there may be some customers with 2-3 embeddings and some customers with 1 million embeddings. You don't really know. So you need to find ways to make your application perform with larger number of independent, isolated customers that don't see each other's data, and also small customers and large customers. The other thing we have to worry about is latency. In a subset of AI applications, latency is so important. If you used GitHub Copilot, you know that it works by autocomplete. If it takes it too long to autocomplete, you've already written your code. Their suggestions are absolutely useless. Grammarly, same thing. You type stuff in English, and once you're done with a paragraph, you want advice. If it takes forever to show up, you've moved on already. It's not going to be all that useful. So you really need, latency matters in these kind of applications. And Inference, while it's not the slowest part of AI, it does take time. So you need to think about how to optimize whatever you can, whether it's optimizing the vector database, whether it's about minimizing distances between the data and the customer and the vectors and the model and all that. And the last thing, if you choose to do fine-tuning, this is a kind of worms, because you need your customers to trust you with their data to fine-tune the model. And you need to find a way to convince them that the model is not going to accidentally give away their trade secret to another customer. So you may need to train a small model for each one of your customers, or maybe the big ones deserve their own specially trained models, and then you have, the cheap tier customers that are actually working off a common model and do not get to this kind of fine-tuning advantage. So you have to figure this out, and this is added complexity on something that was probably the hardest part of doing AI SaaS to start with. So hopefully now you get all the concepts. You know what are generative pre-trained transformer models. You know what is RAG versus fine-tuning. You know what are vectors. You know that vectors are the same as embeddings. And you have some idea of what it takes to actually use them. Next time, I'm going to do a deep dive into a specific example.